If you are new to the channel, then subscribe the channel and press the bell icon for further notification. Okay student, welcome you all to this new lecture in machine series. So today again we will be solving 6 questions starting from question number 192, 93, 94, 95, 96 and then 97. Okay, then let's try to solve these 6 questions. Now if you come to 192, a single phase induction motor draws 12 megawatt power at 0.6 lagging. A capacitor is connected in parallel to the motor to improve the power factor to the combination to 0.8 lagging. Assume the real and reactive power drawn by the motor remains same as before. The reactive power delivered by the capacitor in megawatt. Single phase, so there is no issue, because if you draw phasor diagram, then I will draw phasor diagram for single phase. If it is 3 phase, then you have to make it for single phase because it is phasor diagram. So normally it was taking 12 megawatt at a power factor of 0.6. That means this angle is cos inverse 0.6, which is at an angle of 58.1. So it is of this fashion somehow. Suppose this is your power triangle. Now you want to improve this one. How you will improve this one? Because you are connecting a capacitor that will support some reactive power, so this angle will improve. This angle you want to now make it cos inverse 0.8, that is 36.86. This is always 12, previously also 12, now also. Now you can apply simple trigonometry, height and distance, you know, if you have studied in class 9-10, that you can apply easily. So what will be this length? BD will be 1053.13. this is 53.1 into this 12, so it will be 16 mega bar, this entire thing. Now if you calculate BC will be again 1036.86 into 12, 9 megabar. So this one is the support that is given by the capacitor. So this CD is the capacitor rating, that is 16 minus 7, 9, that is 7 M bar. So that is your option answer. Next, if you come to 193, in a constant V by F control induction machine, the ratio of the V by F maintained constant from 0 to base frequency, where V is the voltage applied to the motor at fundamental frequency F. If the following statement relating to low frequency operation of the motor is true: at low frequency, stator flux decreases from its rated value, motor saturates, the stator flux remain unchanged at its rated value. Now if you can think of, you can think in this way, because this is constant they are maintaining. So if you reduce F also, accordingly V is reduced, so phi is constant. So you may think of it will be option D. But what happens in low frequency, if you are going accurate analysis of this one, so if you reduce F, your V should be reduced. Now once you reduce your V, then because there will be stator drop, then only this V will come to your picture, that means your E2. V is actually what is the induced voltage in the E2 side, that is 4.44 into this one we say. So that is directly, we generally neglect the stator drops. But if you reduce its voltage to low value, then this drop will be you cannot neglect that one. So that means it will be dropping more. Whatever suppose it was 100, so the drops was 2 volt drop was there instead. And also there may be, because load you are not changing, so current will accordingly change, so drop may increase also if you reduce your voltage, or drop may remain same. Suppose if in case of 100, if there is a 2 volt, then the voltage that is coming across to picture is 98. But if you are giving now reducing it to 10, because you have reduced frequency, now if you do, suppose you reduce to 4, so if you now deduct to it is 2, now there is a deduction of 50%, you can say. So this 2 is very significant in terms of 4, where it is less significance if compared to 400. So if you are reducing the voltage with comparison to frequency for very low frequency, because you need low voltage, then these drops plays a big role. Because of these drops, this ratio doesn't remain same, because now it was supposed to have 100. In this case, instead of 100 by F, it was 98 by F, more or less constant. But now it is 4 by F, instead of 4 by F, it will be 2 by F. So you can see it is not constant, it is reduced by half. So that's why what happens, actually the flux decreases from its rated value. So that is your option B. Now in 194, a 3-phase lifting induction motor provided with the commutator winding is shown in the figure. The motor rotates clockwise direction when the rotor winding are closed. Okay. If the rotor winding is open circuited and the system is main to the rotational speed Fr with the slip with the help of prime mover in anti-clockwise direction. Okay, initially it was rotating in clockwise direction. If you give this supply, it was rotating in clockwise direction. Now if you remove this rotor short circuit, if you remove, then it will not rotate. because it rotates due to rotor short circuit. There is a current that produces a torque which tries to kill its source, then it starts rotating, because if you open it, it will not open the rotor circuit, it will not run. EMF will be induced, but it will not run because no current will be passing through, because there is open circuit. Now you are rotating with some prime mover in the anti-clockwise direction. Okay, then the frequency of the voltage across the slip ring is F1 and across the commutator brushes is F2, the value of the F1, F2 respectively. Now this is a very fundamental difference between your slip ring and frequency. If you understand this slip ring and commutator, if you understand the mechanical composition of this one, you can easily answer this one. Now think about this slip ring. Slip ring, actually what happens, slip ring is something, suppose this is my rotor rotating, then you can see these black shades, this one and this is one, or you can see these white strips, 1, 2, 3. So this is slip ring. So one winding will be connected to this slip, another winding will be connected to this one, another winding. So whatever the voltage of that winding, so one thing will be put on this one. So whenever it rotates, the same winding will be connected with that terminal. Suppose I take R terminal, so R terminal is connected every time with that R winding. What happens in R winding, that will actually come. Now what happens in case of this one, that commutator arrangement, commutator, we can think it of that splitting it into two parts. Let me show you. Suppose of this fashion, it is splitted. So one winding will be connected to the one winding will be connected to this one. So one brush is fixed. So when this comes to that side, so this winding is now connected with this brush. When this comes, this winding comes to this brush. So the winding changes. Brush remains same. The same winding is not connected every time. So that's why you got unidirectional current in DC motor with commutator arrangements. So that is the difference here. So in slip ring, so now you see what will be the voltage induced in that EMF. Three-phase stator supply voltage, so which is rotating at synchronous speed. We have applied stator, so stator magnetic field is rotating ns, that is giving frequency of F. So due to which there will be induction in the rotor winding also. At what rate it is cutting, because it is not rotating, it is cutting at the same speed, at the ns speed it is cutting, because nr is 0. So it is cutting at that same speed. So the frequency that is developed here is also F. Now what is happening, you are rotating it now anti-clockwise direction with Fr. Now at what speed it is cutting? F plus Fr. You can think, because it is rotating in just in anti-clockwise direction, rotational speed of Fr with respect to the prime mover. So now it will be cutting at F plus Fr, because if it is not rotating, then it is cutting at. Now if you are cutting it this one, so the EMF that is induced in each phase is Fr, F plus Fr. And when slip ring is connected, then that phase EMF is every time is coming out in the picture. So you will get the actual frequency that is in par phase. In each winding the frequency is this one. So F plus Fr. But what happens in case of commutator arrangement? In case of commutator arrangement, what you are doing, that is of slip ring. So you can see it is either option A or D. Now what happens in commutator? I told you in commutator arrangement that brush remains fixed, but every one time one conductor EMF winding will come, same winding will not come. So the rotation that you are doing, that will be getting nullified, this additional rotation, because even if you rotate, because your commutator brush is fixed, so one time one winding, suppose there are two winding, R, one winding, winding 1, winding 2. So one brush is there. So if it is connected here, so whatever happens this time period, it is coming, next it is coming here. So you can, so what, even if you rotate, it will not feel that there is a new winding is coming. It will see whatever, when winding remains here, whatever you can see there is a separation. That is the insulated. Suppose there is no rotation, so if the brush is connected, it is always connected with this one. Whatever wind happening in this winding, that will also always come. Now even if it is rotates, what happens? First it is connected. Next, when this winding comes here, it is also giving same effect, because it is connected this side. North pole will be suppose of this side. So whatever happens, so this brush will think that only one type of winding is connected here. So this rotation effect will not create that effect, because that has been nullified. So in commutator arrangement you will get only F. So that's why it is option A. So you have to understand the basic mechanical difference between slip ring and commutator. give you clear idea of this one, 194. Next, if you come to 195, a single phase induction motor is provided with capacitor and centrifugal switch in series with auxiliary winding. The switch is expected to operate at 0.7 ns, but due to malfunction the switch fails to operate. This torque speed characteristics of the motor. Okay, why this auxiliary switch is given? Because single phase motor is not a self-starting, so you give a auxiliary switch which splits actually two phases. Once single phase is split into two phases and it starts as a polyphase winding, so you get some starting torque. After that you remove that centrifugal switch, it comes to original, torque gets reduced because from polyphase to it comes down to single phase. So this is the original characteristics of a single phase induction motor if the centrifugal switch operates. If it doesn't operate, then it will maintain this one. Doesn't operate means it will look like a polyphase machine. So polyphase machine torque speed characteristics this one, single phase machine torque speed characteristics is this one. If you don't give centrifugal, it will be like this. At the starting there will be no torque, it will not start self-starting. That's why we started with this way. This is your starting torque, so that it gets some starting torque, then it makes it like polyphase, and after that it becomes single phase. So if that centrifugal switch doesn't operate, that means it will always look like a polyphase. So it will be like option C, normal polyphase induction machine. Now in question number 196, the torque speed characteristics of TM and TL of the two cases are shown in figure AB. The load torque is equal to the motor torque at point PQRS. The stable operating we have already discussed. If your stable operating point, how you will check? You increase your speed little bit, speed you increase. If you increase your speed, by inherent that motor torque or electromagnetic torque should be, because speed is increased, so you want to bring it to back, so it should be less than your TL. Then automatically speed will come back to its original position, then it will be stable. If this happens, then it will be stable. And similarly, if your speed is less, then your TM should be more than your load torque, so that it will bring it back to its original speed. So you see here, this speed is increasing in this direction. Okay, so if you increase your speed a little bit, suppose from P, if you increase your speed somewhere here, then what is that? This much is your load torque and this much is your electromechanical torque, motor torque. So motor torque is less than load torque. So if speed is increased, so because your motor torque is less, so obviously speed will come back to its original position. So somehow if there is any disturbance, speed is increased also, the motor will automatically tend being back it to P, because if it increased here, if it comes here, then motor torque is becoming less than load torque. So obviously there will be reduction in the speed. So it will come to this position because motor cannot generate that much torque. You are giving more pressure on the motor. So obviously speed will come back to its original position. So inherently it will come back to this. So obviously P is a stable position, and vice versa will be here in less if your speed is reduced also, then motor torque is more, so it will bring the speed back to its original position. So obviously P will be one option. So obviously A or B, it will be either these two. Now if you come to Q, if you increase your speed here, now you see your TM is more than TL. So if you increase your speed, then also your motor torque is more. So it will further increase this one. So it will keep on increasing. It will not come back to Q. So Q is not a stable point. Similarly here. Now if you see, if you increase your speed a little bit here, you come to this position. This is your TL. This is your TM. This graph is for TM. This graph is. So you can see your TM is more than TL. If your speed is increased more than R beyond this position. So if your motor torque is more than load torque, so it will keep on increasing the speed, it will never come back to this one. So R is not a stable point, so obviously it is P and S. You check S, increase your speed a little bit. Now you see this is your motor torque, this much, and your load torque is more. So motor torque is less, load torque is more. So obviously because motor torque, generated torque is less than load torque, so speed will come back to its original position, so it will come back to S. So that's why option B is the correct option, 196. This is given as 3-phase 197 50 Hz square wave 6-step VSI fits 3-phase 4-pole induction motor. The VSI line voltage has a dominant fifth harmonic component. The operating slip of the motor with respect to fundamental component is 0.04. The slip of the motor with respect to fifth harmonic of the voltage. So I have already explained in case of fifth harmonic, because so a number of pole that seen by the rotor will be increased. So your NS will be now 120 into 50 by pole will be more. So if it is originally it was 4 pole, because of fifth harmonic it will be of this fashion. So your NS, it will look like this due to this fifth harmonic. Rotor will feel like this. So And you have already seen, due to this negative sequence, the rotation that is developed, that is in reverse direction. So your slip will be equal to ns minus this ns by 5 divided by ns. So your speed will be equal to, now if you solve it, it will be 1500 minus 1500, and if you solve it, you will find your answer is equal to 1.2.
If you like the video, then press the like button and please give your valuable comments in the comment section.